Now the next important thing is that the notion of a radon measure. So this is the basic foundational thing to go into the realm of Rees representation theorem. So eventually, my goal is to arrive at the Rees representation theorem, which is a very useful and powerful theorem, and obviously it's very beautiful. So what is radon measure? So suppose you have a set X. You also have some topology on the set X. And suppose this space is Hausdorff. And most of the nice and useful topological space that are studied in mathematics are mostly Hausdorff. So suppose X is a topological space which have a Hausdorff topology, and you also have a measure on Borel sets of X. Now, what do I mean by Borel sets of X? So I have to explain what is this Borel sets. So since you have a topology on X, so you have a notion of open set, right? You have defined what is an open set in X. So basically the members of the subcollection that you have chosen to define a topology on X, those members are called open sets. And then what is a Borel sigma algebra? A Borel sigma algebra is a sigma algebra generated by open subsets of X. So now what is sigma algebra? Sigma algebra is a particular collection of subsets of X which follows some particular rules. What are the rules? It has to be closed under taking complements and countable unions. So basically, that's what we mean by a sigma algebra on a subset X. Now, how do you generate a sigma algebra with some given open subsets? So basically, there is some collection of open subsets since you have defined a topology on X. Then you take their arbitrary unions and also their complement. You also have to take the complement. So basically, also you are taking the closed subsets of X. You take this whole collection, so that will give you a sigma. So if you want a formal and precise definition of a sigma algebra, then I want to recall the definition. So a sigma algebra on a set is a non-empty collection of subsets which is closed under complement, countable unions, and countable intersections. Yeah, that's what I said. So given some open subset on X, you take their complement. So you also include the closed sets. Remember that in a topological space, a closed set is by definition a complement of the open set. So when you are taking complements, you are also allowing the closed sets, and then you are taking countable unions. So if you take union of open set, that will remain open, and also you are allowing countable intersections. So that is an important thing. Yes, countable intersection of open set may not be open, right? So so you may land up in some subset which is not already in your topology. Yeah. So the upshot is that just remember in this way, in the following way, that you have some open subset of X, you take their complements, you take their countable union, you take their countable intersection, and that will give you a sigma algebra. So that is your Borel sigma algebra. And the members of the Borel sigma algebra are called Borel sets of X. And then you have a measure on Borel sets of X. So ultimately what you have a set X, you have a topology on the set X, you have a measure on the set X, and now we are ready to define what is Radon measure. So the main essence of the Radon measure is that we want to make these two notions compatible with each other. So that is a main keyword. So let me write down. This is the key idea. It's compatibility of topology and measure. So the measure you are defining in some sense is compatible with the topology of the space. Now this notion of compatibility is captured by some precise conditions. So what are those conditions? So let me give you some intuition. So recall that uh, in the real line, on the real line, if you take the standard Lebesgue measure, then what is the measure of the closed interval AB, where A and B are both finite? A and B, I'm not saying A and B are infinite. A and B are two finite numbers, and I look at the closed interval A comma B. Then what is the standard Lebesgue measure of this interval? So that is just B minus A, right? So basically, what we call the length of this interval is B minus A. And obviously, this is finite, right? Now, if you look at the topology of this closed interval, closed AB, this interval. So topologically, this is compact, right? I hope you know the definition of compactness already. In fact, on the real line, you have a nice characterization of the compact sets. Compact subsets are basically those subsets which are closed and bounded. This is some famous Heine-Borel theorem. So, in some sense, I can say that. In fact, you can actually say that mu of any compact set is finite, isn't it? Because any compact set is basically closed and bounded. So I can put any compact set inside some big closed interval, and then measure of my compact set X will be less than or equal to measure of the closed interval AB, and which is obviously finite, which is in fact B minus A. So basically, the first important thing is that measure of any compact set is finite. So that is the first thing. So okay, one thing I want to emphasize is that in the definition of measure, I said that this measure can only be a non-negative real number. But in fact, sometimes infinity is also allowed. So what we call as extended positive real number. So measure of some particular subset can also be infinite in some model of measurable space. You can create a measure on measurable subsets of X following these rules, where some sets might have infinite measure. Sometimes this is known as, extended measure. So basically, measures which are extended to extended real numbers. By extended real number, I mean attaching infinity to the set of real numbers. But for radon measure, this is not allowed for compact sets. So compact sets should have finite measure. And for the intuition, I just have given an example, which is the most basic and common example, which is a standard real line is standard Lebesgue measure. So that is the first condition for a measure to be called a radon measure. The next thing is that, okay, so let me add another page. Yeah. Again, look at the real line, and suppose I have this set closed AB, a closed interval AB, and I can distort this closed set a little bit to make it an open set. So if I allow the error of length 1 by n on both sides, suppose this length is 1 by n, so basically I'm trying to say is that the closed interval AB is contained in the open interval a minus 1 over n comma b plus 1 over n. So basically this closed set can be put inside an open set. In other words, you can say this closed interval can be approximated by an open interval. And if I take n larger and larger, this 1 by n will approach 0. That means my approximation will get better and better. And the measure of the interval, the open interval, a minus 1 by n plus b plus 1 by n, which is the length of the interval, that is b minus a plus 2 by n, will approach b minus a as n tends to infinity, that is 1 by n tends to 0. It will approach b minus a, which is nothing but the length of the interval mu of ab. So basically, what is the main upshot? The main upshot is that the measure of the closed interval AB can be approximated by measure of the open interval containing that closed interval. So the measure can be approximated by the measure of the open set containing that particular set. So this notion is called outer regularity. You can already see that in this notion of outer regularity, I mean, whatever we have said to define what is outer regularity, already this topology and measure, these two concepts are interacting with each other. Because you are approximating the measure of the closed interval AB by the measure of the open sets that contain that particular subset. So whenever I am approximating the measure by some open set, that means I am using the topology of the space X. So these two concepts, topology and measures, are already seen to be interacting with each other. So that is the notion of the outer regularity. So right now I'm just saying these things intuitively. Just in a few moments I will define this in a formal mathematical language. So this is outer regularity. Then there is another thing which is known as inner regularity. So again, let's say I take an open set, open interval, let's say AB, and then I can take a closed interval inside it, which is obviously closed and bounded. So this open interval AB contains the closed interval, I can say a plus 1 by n and b minus 1 by n. I'm allowing this error to be 1 by n on both sides. So what is the measure of the open interval AB? Limit measure, which is b minus a. And what is the measure of the closed set that I am approximating with? So measure of a plus 1 by n comma b minus 1 by n is just how much? B minus a minus 2 over n. And again, you can see that as n tends to infinity, this approaches b minus. So that means mu of the open interval AB can be approximated by compact sets. By compact sets that are sitting inside the subset that we are interested in. So again, you can see that measure and topology, these two things are interacting with each other. So this is the notion of inner regularity. So now you can write this in a write these three things in a formal manner. The first thing is that mu of any compact set is finite. Second thing is that mu of any set A is infinimum of mu of mu, where U is an open set containing A. So that means what I've already said intuitively, that you're approximating from outside using open sets. Just uh, just recall this picture, that this picture is very useful. This is the notion of outer regularity. I'm approximating from outside by using open intervals that contains my given clothing. So the approximation is happening from outside. That's why it's outer regularity. In the formal language, you write this thing in this way. That measure of any set is infinimum of measure of all those open sets that contain that given set. And what is the third thing? That is inner regularity. So this is approximation from inside. So this is supremum over mu of K, where K is contained inside A. So in the second condition, U was containing A, but here K is contained inside A. The approximation is happening from inside. That's why it is called inner regularity. And K compact. So you have a Hausdorff topology on a set X, and then you have a measure which satisfies these three conditions. And that is your Radon measure. So the second condition is that the second condition is known as the outer regularity on Borel sets. What is Borel set? I have said it earlier. Any element of the Borel sigma algebra. What is Borel sigma algebra? The sigma algebra generated by open subsets of X. And of course, we can talk about open subsets of X since already a topology on X is given. Already a topology is defined. So just remember this in a hierarchical way, that you have a topology, you have a notion of open subset, you can generate a sigma algebra using this open subset. That is a Borel sigma algebra. And the members of the Borel sigma algebra are called Borel set. And on the Borel sets, you have outer regularity. So that means you can approximate the measure of each Borel set from outside using open sets. So that is the outer regularity on Borel sets. And the last condition is that it's called inner regularity. Inner regularity on open set. Okay. So now let me summarize what we have discussed in this video. So I will not go into the Rees representation theorem in this video itself because it will be very long. So probably I will make 2 or 3 more videos to go into the main thing that I want to focus, the Rees representation theorem. So in this video I have just developed the basic foundation, which is the notion of a radon measure. So the main idea of the radon measure is that there is a topology and there is a measure on a set X, and you want to make these two notions compatible. And so how do you make those two things compatible? By using these 3 conditions. The measure should be finite on compact sets. We can approximate the measure of any Borel set from outside using open set. You can approximate measure of any open subset from inside using compact set. There is inner regularity on open set. And any measure on a Hausdorff topological space which satisfies these 3 conditions is called a Radon measure. Most useful measures that are used in different areas of mathematics and in number theory and in many other areas, a very important measure is what is known as R measure. And that is also a Radon measure. So maybe in later videos I will discuss this thing in more detail. For now, for now you should be very comfortable with the basic concepts. I have also given motivations to how to remember this condition. So always remember these basic examples on the real line. That is good enough to recall. Even if you forget some conditions, you can recall using this motivation. Okay, that's it for today. Bye.